So hello everyone, hope you all are doing well. So in today's video, we will be covering our blind series 25th question, which is unique paths. Okay, so let's read the problem statement. So there is a robot on M cross N grid. The robot is initially located at the top left corner, which is grid 0, 0, which is this, here our robot. And the robot tries to move to the bottom right corner, that is grid M minus 1, N minus 1, which is this one. The robot can only move either down or right at any point in time. So we have two choices. The robot can either move to right side or it can move to downside at any position. The, we have given our two integer m and n. Return the number of possible unique paths that the robot can take to reach the bottom right corner, which is this one. The test cases are generated so that the answer will be less than or equal to 2 into 10 to the power 9, which means we don't have to worry about any integer overflow. Okay, so let's see the solution of this question. Okay, so let's say we are given m and n. M indicating your number of rows and n indicating your number of columns, and this is the 3 by 3 grid we got, which is m cross n grid. Okay, and this is a tiny robot, and this is the finish point we have to reach. Our aim is to reach to this position. Okay, move our robot to this position, and we have two choices to do that. Either we can move to the right side, okay, or either we can move to downside. Okay, at any position we can choose either right or down, and what we have to do is we have to count number of ways to reach, to make this robot to reach this position. So let's see how we can do this. Let's say first of all we move right, then again right, then we move down, again down. So like this we reach to our destination. Let's say my one is indicating my left left movement and two is indicating my down movement. So first of all I move, I mean this right movement, okay, not left. So let's say first of all what I do, I move first right, then again right, then down, then again down. Okay, so this is one way I can reach my finishing point. Another way we can do is, first of all I go down, then again down, then right, then again right. So like this way also I can move to my finishing point. For what I do is, first of all I move down, then again down, then right, then right. Okay, this is another way. The third way can be, first of all I move right, okay, then I move down, then right, then down. Okay, like this way also I reach my finishing point. What I do is, first of all I move right, then down, then right, then down. So this right, down, right, and down. I move to this finishing point. Then another way can be, first of all I move down, then right, then down, then right. Okay, this way also I can move to my finishing point. So what I do is, first of all I move down, then right, then down, then right. Okay, now let's see what other way we can move. So let's say first of all we move down, first of all move right, then down, then right. Okay, like this way also we can reach to our destination. So what we do is, first of all move to right, then down and right. Okay, and is there any other way we can move to this position? Okay, yeah, there is one way. Like first of all we move down, then right, then again right, then down. Okay, this way also we get to our finishing point. First of all we move down, then right, then again right, and down. Okay, so is there any more ways to reach this final point? I don't think any there is any more ways to reach to our finishing point. So there are total 6 ways to reach the from this initial point to this final point. Okay, there's total six. Let me see if there are actually 6 ways or there are more ways. Okay, yeah. So you can see here there are total 6 ways to reach our destination. So we are right. So these are these 6 ways we can reach from this initial position to the final position. This. So how can we implement this approach into our code? So it's very simple. What we have to do is we have to check at any point in time, either by going right or down, can we reach to a final destination or not. For example, if our robot at this position, so can he reach to this position or not? Okay, so he can reach to this position. If it is here, so he can again reach to this position by going down then right. So that's what we have to calculate. And again, if our robot is at this position, so he can't go to the right side because it will go out of the boundary. So I also have to check for this condition. If R goes out of the boundary, so I will neglect that condition and I will see if there any other way our robot can move. Like we have only 2 ways. First of all, he can go to either right side or he can go to right downside. If it can't go to right side, then we simply restrict it and tries to see if either it can go to the downside or not. If it can't go to the right side, then we simply go to down. And if at this position, if it can't go to the downside, so we simply goes to the right side. Like in this function, this condition will handle this case of the out out of boundary condition. Okay, if any point of time, like our indexing will be from 0 1 2. Okay, if any point of time my I reaches to the third index or m reaches to or j reaches to the end index, I simply return 0 because this means my robot is going out of the boundary. So I will not go any further from here. So I will return. And this condition checks if my robot is on the finishing line or not. So this position is 2 comma 2, which is m minus 1 and n minus 1. If my j and I both are on 2 comma 2, it means my robot is actually in the finishing line. So there is one way to reach this finishing point. So I simply return one. At this line, I am choosing 2 ways my robot can move. I plus 1 indicates my robot is moving to the right side, and j plus 1 is indicating my robot is moving downside. So at all point of time, I am checking how many ways how many unique paths I can take to reach the finishing position. Let's say I am at the 0, 0 position. Okay, then what I do, I reach to 1, 0 position. Okay, then here from here also I reach to 2, 0. Then I can't go beyond this because 3 will occur and 3 is out of the boundary. So it will simply return me 0. So at this time, this function gives me 0. Then I go to the downside, then it will become 2, 1, and this goes on. So it becomes a tree-like structure. Okay, like this. Then I will go from here 1, 1. Then here is 0, 2. You can see it's become like a binary tree type structure. Okay, and and as they return the solution to the upper parent and finally I got the answer here. Okay, at this same position, and I will return that answer. So let's try to implement this in our code. I will simply create a new function, if1. It will take the initial index of my robot. Okay, and the boundaries of the grid. First of all, I will handle my boundary condition. If my robot reaches to either my m or n, so I will simply return 0. And if my robot reaches to the finishing line, okay, so I will simply return 1. And this is not and this is all. Okay, And if it is not on the finishing line or not out of boundary, so I have two choices. Either I can go to right side or either I can go to the left side. Okay, first of all, I will go to the right side. No, I mean the downside. Okay, here my robot is moving on downwards, and here my robot is moving to the right. And I will simply call this function and return the output it is giving me. Okay, initially my robot is at 0 comma 0 position, and m comma n is the grid size. Let's return this. Okay, so it's giving me the right answer. So let's try to submit this. So here I got TLE. Well, it is because at any position I have two choices. Either I can go to the right side or downside. It means, and then again on the next position I have two choices. Either I can go to the downside or right side. So the time complexity of this code, as you can see here, I at any position I can either move to the right side or the downside, and then at those position also again I will move to the right side or downside. So as you can see, at every position I am taking two choices. Okay, and the total size of this grid is n cross m cross n. It means the time complexity of this code will be to the power m cross n, which is very large because m and n can be maximum up to 100. So it means the time complexity of this code is 2 raised to the power 10 raised to the power 4, which is too much if we apply this brute force approach. So is there any way to optimize this code? So yes, we can optimize this code from the from 2 raised to the power m cross n to m cross n by using dynamic programming. So let's see how can we do this. So it is a tree-like structure that I made, which indicates the movement of my robot. When going to the left side, it indicates that my robot is moving downwards, and to the right side, it indicates robot is moving to the right side. As you can see, if at this position 2 comma 0, if my robot moves to the downside again, so it will move to 3 comma 0, and it will reach my boundary condition here. So I will not show that condition. The and also you can see there are total 6 ways to reach 2 comma 2. Here the 6 ways I get. The main motive of showing this is that, see, as you can see here, this structure and this structure is repeating, and this structure and this structure is also repeating. So at this time also we have to calculate at this point 11, 1 comma 1, we have to calculate how many ways, such possible ways are there to reach the finish point. And again we also have to do the same repetition to find how many ways we can reach from this position to the final position. And again the same we have to do, so the same calculation we have to do again at 1 comma 2 position, and here also again we have to do 1 comma at 1 comma 2 position. So can we simply save the ways? As you can see, there are two ways to reach the final position if we start from this 1 comma 1. So can I simply save this 2 at this position, and when I compute the same at this position, I simply use this value which I stored earlier. So I don't have to compute it again and again. Okay. So this is what we do through dynamic programming. Okay. So we don't have to compute again and again when we reach to this position. And again at in this position I we have one way to reach, and when I move again come to this position, so I simply return this. Okay, so how can we do that? Let's see. Okay, so first of all, we create a vector which is dp array. Let's name it dp m cross n and initialize it with -1 and send it to our function and receive it here. Now I will store the value I get from this particular IHR index. If first of all I will compute at this particular I comma jth index, what is the how many ways I can get to the finishing point, and the number of ways I will then store in my dp my this dp array. Okay, and for later stages, if ever I encounter the same index again, okay, so it's obvious that it will not be -1, it will be 0 or some non-zero values. So instead of recomputing the same process, I can simply utilize the value that I stored of this index in the DP. Here I stored that particular index, and if I get the same index again, so I can utilize the value which I stored in the DP. Okay, and I can simply return that particular value. Okay, so this is all our code. So let's try to run this code. Okay, okay, we have to pass DP also here. Okay, so it's giving me the right answer. So let's try to submit it. So it got submitted. Okay, and the time complexity of this code is m cross n. Okay, it is because we only have to visit a particular index only once, and if we visit that same index in future, so else of computing for that particular index, that how many ways we can reach through that index to a finishing point, we simply utilize the dp array, the value that we store in the dp array, which saves the result for that particular index, that how many ways from that particular index we can reach to the finishing point. Okay, simply we utilize that else of computing it. So this will reduce our time complexity from 2 to the power n to m cross n. So that's all for today. Hope you understand the approach. You will get the source code of these in our GitHub. You can check the description for the link. So I will meet you on the next video.